Welcome to Future Talk. On today's program, we're going to talk about the Higgs boson, which is probably the most important discovery in particle physics in the last several decades. The Higgs boson was discovered at CERN, the huge nuclear research facility near Geneva, Switzerland. It was discovered as part of the ATLAS experiment, which is a collaboration between many scientific institutions around the world. We're going to talk about why scientists are so excited about the Higgs boson. We'll discuss the current state of particle physics from both the experimental and theoretical perspectives, and how all of this research may affect you. I have two guests. Su Dong is an experimental particle physicist and head of the ATLAS experiment group at the Stanford Linear Accelerator Center, also known as SLAC. SLAC is one of the participating institutions in the ATLAS experiment. Peter Graham is a theoretical particle physicist who's worked at SLAC and is now in the Stanford Physics Department, where he's already made some important contributions to particle theory. I'm going to be talking to my guests in just a few minutes, but first, I recently interviewed another physicist, Professor Val O'Shea from the University of Glasgow in Scotland, who's been working on the ATLAS experiment for the past 20 years. I interviewed him via Skype. Here's that interview. O'Shea, welcome to Future Talk.
Thank you, Martin. It's my pleasure to be here.
Now, the world of physics has had a lot of excitement recently because of the Higgs boson. What's the excitement all about?
Well, the recent discovery announced at CERN is the discovery of the last of the particles, in actual fact, that make up the equation that fit the standard model of particle physics, if you like. So, given that this has taken 20 years of 3,500 people's lives on my experiment and a similar amount of time for the other experiment at CERN, this is a considerable achievement.
Now, when you say that it's filled in the standard model, what exactly is that standard model?
The standard model, in a nutshell, is a series of mathematical equations that describe how matter interacts with itself and gives us what we have today, both everything that you see around you and everything that's in the universe.
So this is about fundamental properties of the universe, the most basic particles of matter that we can detect?
Yes, and this goes right back to, if you like, the Big Bang, the start of time, for want of a better way of describing it.
Now, the Higgs boson is a type of boson. What's a boson in general? What are the basic properties of a boson?
The basic properties of a boson are that it mediates forces between the particles that make up matter. And so you have the photon, which gives the electromagnetic forces, and the Higgs boson, its particular thing is that it gives mass to all of the other particles.
When you say that it gives mass, what does that mean? Does that mean other particles don't have mass unless a Higgs boson is nearby?
They have mass in the Higgs field. So this is the thing that gives them mass. And essentially, when you look at mass, it's something that you can feel in your hand because of the weight of it. But how you describe that mathematically is quite different, and so this is where the Higgs comes in.
Now, your field is designing equipment to do scientific experiments to look for these particles. Could you describe in a nutshell what this equipment has to do in order to show a particle such as the Higgs boson?
Okay. In the experiment that we do, bunches of protons at very, very high energy circulate in a ring, which is 27 kilometers long, and bunches of protons are brought into collision with each other once every 25 nanoseconds, which is 40 million times a second. And some of those protons interact with the protons from the other bunch, and they release particles of very, very high energy that propagate through the experiment. So the experiment, in actual fact, tracks all of these individual particles and measures their energy, and then you try and reconstruct what happens when the original protons or parts of the protons interacted with each other.
So you're saying that protons are shot at each other at very high speeds, and then they break apart, and then how do you follow the results? This must happen extremely fast.
Yes. All of the particles essentially are traveling at the speed of light. So when the particles break apart at very, very high energy, at the center of the experiment there's a very large magnetic field, because the whole experiment is in a big toroidal magnet. And this bends particles of charge as they travel through the matter. And as each of the fragments of the collision travel through the detector, there are detector elements that track the passage of the particles with great precision. And here we're talking tens of microns. A micron is a millionth of a meter over distances of tens of meters. So it's very, very high precision tracking, very high precision measurement of the way the particles bend in the magnetic field, because that tells you about the charge of the particle and its energy. And finally, all of the particles are stopped in a calorimeter, which is a device for measuring the energy of each of these fragments.
Now, once you have a Higgs boson or any type of boson, does that particle last, or does it just instantly vanish and disappear?
Oh, these particles have lifetimes of a millionth of a second. So they have a very, very fleeting existence. And in actual fact, when we do the experiment that looks for these, we can't actually see the particle itself. What we see are the products that decay from it. I think one of the big things about this is, while the Higgs boson itself will take some time to have an impact on society, a lot of the technologies that were developed to enable the experiments to take place will have a much, much more immediate effect on society. If you look, for example, at the World Wide Web, which was invented at CERN as a means of getting scientists to be able, in distant communities, to be able to communicate more effectively with each other. This has had a tremendous effect on society over the last 15 years, since it became commonplace. There are also aspects of the technology that we're working on that will have big impacts on medicine and diagnostic medicine, and on issues like national security.
We're back in the studio, and that was my interview with Val O'Shea from the University of Glasgow in Scotland. Now I'm here with my two guests, Sue Dong, experimental particle physicist from SLAC, also Peter Graham, theoretical particle physicist from Stanford Physics Department. Great to have both of you on the show. Looking forward to an interesting conversation.
Yeah, thank you for inviting us, and very glad to be here.
Yeah, thank you.
Sue Dong, let me start with you. I asked Val O'Shea the same question, but I'd like to get your view. Why is the Higgs boson causing so much excitement in the world of physics? Why is this such a big deal?
Well, interestingly enough, I think theoretically it was the last piece of the standard model, actually putting the whole theory together. And it's also the last piece we actually found experimentally, and it took something like 30-some years to find it and to finally put the whole picture together. And so it was, we almost assumed it's been there and should be there, but it is a fact that eventually you reached that point after seeing this last piece. Of course, is a big excitement for all the people actually looking, doing the experiments or actually making this happen.
Why did it take so long to find it? I think Peter Higgs, the British physicist, first postulated it maybe around 1964. Why was it so hard to find?
The way to produce them, unfortunately, is actually not so easy. You need machines, actually accelerators of very high energy, and also the rate of producing them, unfortunately, is not high enough to allow you to fish them out very easily from the experiment. And even at LHC, when you produce them at a high enough rate, there are also a lot of other things actually produced with it, and you actually have to piece out all the background you don't want and try to find this in the middle of a big pile of debris, let's say.
We're going to talk about the ATLAS experiment some more, but first we have a short video illustrating how the ATLAS program works. Let's go ahead and roll that tape and then we'll be back.
According to the Standard Model, all the elementary particles should be massless. The current best theory to explain how these particles attain their mass is called the Higgs mechanism. This is a simple demonstration of how the Higgs mechanism functions. It states that there is a scalar Higgs field which permeates all parts of the universe. Particles with no mass, such as the photon, do not interact with the Higgs field at all, maintaining their kinetic energy and passing through at the speed of light. A particle with mass, such as a quark, interacts with the Higgs field, which slows it down and converts some of its kinetic energy into what we know of as mass. In order to prove the presence of the Higgs field, the Higgs boson must be created and detected. This, however, has proven to be a difficult task, as the Higgs boson is predicted to be a massive particle, requiring huge amounts of energy to produce. The ATLAS detector is our tool for detecting the Higgs. It is situated at CERN in Geneva, Switzerland, and will be used to detect the high-energy collisions produced by the Large Hadron Collider. It measures 44 meters long, 25 meters in diameter, and weighs in at 7,000 tons. Two beams of protons will be accelerated in opposite directions close to the speed of light and collided at the center of ATLAS. How do you create a massive particle such as the Higgs from only two small protons? This comes down to Einstein's famous equation E equals mc squared, which tells us that mass is just another form of energy. By speeding up the protons, they acquire additional kinetic energy. The protons at the LHC are accelerated to 99.999999% the speed of light and acquire a total energy of 7 tera electron volts. This, combined with the energy of the other proton traveling in the other direction, produces a collision with the energy of 14 tera electron volts. Upon a collision, all this energy becomes hundreds of different kinds of particles. It is in these conditions which, if it exists, the Higgs boson will be created by the LHC and detected by ATLAS.
Well, that was our video about the ATLAS project. You know, I didn't quite understand the relationship between the Higgs boson and the Higgs boson field. Do you need a Higgs boson to have a Higgs boson field, or can you have the field without the boson?
The one way to see it is the Higgs boson itself is some kind of excitation of the field, and maybe actually Peter maybe is better one of the theorists actually comment on that particular aspect of that.
Okay, yeah, go ahead.
Sure. So yeah, actually that's the right way to say it. If you have the Higgs field everywhere, it's maybe a bit like having a pool in your backyard. That pool is there. You know, if you'll fall into it, you'll feel it. But mostly the surface just lies flat. The Higgs boson, the actual particle that they're trying to produce at the LHC, is like a little ripple on the surface of that water. So if you threw a rock into that water, for example, you would produce this ripple, this excitation on the surface. That's the particle. That's the Higgs boson. And it's a necessary product of the field, but the field is what's all around us, invisible all the time. And you only get the particle if you work really hard and produce this LHC, which is this great machine.
And the LHC is the Large Hadron Collider. What's that about? Can you tell me a little bit about the Large Hadron Collider?
Yes, so the Large Hadron Collider is a ring of 27 kilometers long, and the reason being that large is because the energy of the beams actually is so high that it's like a very fast train. You cannot really take sharp bends. You have to really use very large magnets to actually keep them in that ring. And the reason for the high energy is the higher the energy you take these protons, make them collide, then the more chances are that they can actually creating something interesting at a high enough mass, like the Higgs boson mass, to actually make more of those particles for you to actually detect them. So that's where the Large Hadron Collider was built for. And the other problem is that when you go to higher energies, the cross-section, which means that the interaction rate is actually, for a lot of other things, actually going down to some level. So you have to actually get a very high intensity. So each beam actually is equivalent to several trucks worth of kinetic energy in the beam to actually allow you to produce enough events or enough these interesting interactions for you allow to actually to see them.
Now this is really a huge machine. In fact, we have a picture of the Atlas detector. Can we show that picture, please? Basically, we should have a slide of that. Okay, so there it is. And just to see the size of it, if you look really closely, there are two little people standing on top of the central shaft between that propeller-like structure on the left and the main body of the detector. Those two little figures are people, so that's just showing the size of the whole thing. Is it possible to get the technology simpler so someday we'll have personal colliders like we have personal computers?
It may be a little bit difficult because the main reason it's been that large is that for very high energy particle, it's very penetrating. From all the material, you take lead, you take gold, it still travels a great deal of length through those material before it stops. And when we try to measure the energy, we want to contain all the showering of the particle within that material. So unfortunately, that you have to make the material thick enough so you can contain all the shower it made, so you can measure all the energy that actually got dumped into it. That's the reason it's been so large.
Now, how do you get these particles to move at such a high speed, just a hair below the speed of light itself?
Right, this is the role of the accelerator, and for that there are various technologies being used to actually to push the particle at a higher and higher energy through the superconducting magnet to actually accelerate them. But of course, when you accelerate, there are a lot of other effects you have to take care of, such as there are many particles together, and they tend to repel each other. You have to keep them under control and so on. That's why it's a very complex machinery to actually allow you to take that high energy.
Well, we spent several decades trying to find the Higgs boson. Now we found it, so are we done? Or are we looking for other things now?
Well, at the moment, I think there are many things we're unhappy with the theory, and I think Peter can comment later, is that we want to see what's beyond that. But for the moment, I think there's at least one piece of information we may talk about, like dark matter, which is outside this bound of the standard model. And so we hopefully can use the Higgs boson as a stepping stone to measure how the behavior the behavior of the Higgs boson or things related to it, to well enough so maybe we can get some hint whether there's some more stories beyond the standard model, this is standard as the last piece in front of us.
Okay. So now, Peter, let's talk about the theoretical side a little bit. Particle physics is about understanding the most fundamental objects in the universe. So my understanding is that we have matter and energy, which are roughly interchangeable with each other. But is there anything that's more basic than anything else?
That's a great question. In a sense, I would say the answer is always we don't know. That's why we build machines like the LHC to find out what is the most fundamental thing. We've always looked at shorter and shorter distance scales, right? You build microscopes and then colliders to look at shorter and shorter distance scales. But right now, the standard model, the theory that seems to be working, is that everything we see in the universe is made out of particles. And those are the fundamental objects of our theory. So everything around you, whether it's this table or light shining on you or the stars, it's all particles. Every force is transmitted by particles. Gravity is probably transmitted by a particle. So that's probably the most fundamental object.
Now we have another still picture which I'd like to bring up, which shows some aspects of the standard model. Do we have that other image? There it is. So we have quarks, leptons, and forces, and that's the Higgs boson in the middle there. So, so what is this chart really telling us?
Well, this actually is very neat because it summarizes essentially the entire universe. All the fundamental laws of physics are contained in that little graphic. We believe everything we see can be explained by just those particles. You see just a handful of particles. For example, all of our matter is made out of those quarks. They make up the nucleus of the atom, or the electron going around it. And all the interactions, everything, all the complex stuff that gives rise to stars shining and everything, comes from those four fundamental forces: the gravity, electromagnetism, the strong and weak nuclear forces. So as far as we've seen so far, that explains everything. That explains every experiment we've ever done. And now it was actually a really great theoretical triumph. You could see all these other particles of the standard model I would say at the same time the discovery of the Higgs boson is a great experimental triumph, it was also a great triumph for the theorists because they saw all these particles of the Standard Model and they realized there had to be one missing. You tried to fit them into this nice, tight mathematical framework, and you realized there had to be a Higgs boson. And now, several decades later, it's been found experimentally, so that's sort of a major triumph.
Now, talking about basic stuff, what about space itself? Is space something basic? Is space just emptiness, or is it some kind of material, some kind of substance that can be manipulated?
Yeah, that's a great question. And actually, you know, that was the real change between Newton and Einstein. For Newton, space was a background empty stage, and particles just ran around on top of it. But Einstein, I think maybe the right way to describe his great realization, his general theory of gravity, of relativity, was that actually, no, space is dynamical. Space can move itself. Space is sort of on equal footing with everything else. So actually, we believe all the time when the Earth moves through space, it's warping, it's pulling on the space around it, and actually that's what's causing gravity.
So is that what a field is? When you say that there's a field, is a field just some kind of bending of space?
Oh, actually, that's a great question. I would say it's sort of the other way around. Space is a field. Space is just one example of a field. The Higgs boson is another example. And they all can warp and bend and move in funny ways. And sort of the really cool thing is that space is another one of those. It is a field like that, and that's all gravity is.
Now, are matter and energy basically interchangeable? And what makes one change? Are they basically the same thing and we just look at it from a different aspect each time, or does it really change itself?
Sort of. Einstein taught us matter is just another form of energy, right? His famous equation, E equals mc squared, basically says matter, mass, is one type of energy. So at the LHC, if you want to make a particle like the Higgs boson, which has a very high mass, you take two very light particles and bang them together. Now, normally, if you're combining, jars of sand or bottles of water or something, you can't get more mass than you started with. But at the LHC, they do. They take these protons and they bang them together to get something with much more mass. That's only possible because they accelerate them to such high energies, and then they convert that energy into the mass of the Higgs boson. So they are basically interchangeable with a lot of work by dedicated experimentalists.
So what's the hottest work in experimental particle physics right now, or theoretical particle physicists? What's the next step that you're looking for? Either one of you can answer that.
Actually, for the experiment at the moment, as I said, the immediate step is now we produced some amount of the Higgs-like particle. Then we need to see there are more data coming. So we need to analyze this state to see is it really the Higgs boson, or is maybe the cousins of it, or something else. So we need to look at the property of this particle. But behind that, as I mentioned, there are other things we're not happy with the theory. We're missing pieces of things beyond to explain all of this, why it's actually come together like this. Then for those things, we're actually looking for additional new particles, which have a completely different behavior from Higgs, but more like the partner of the existing particles. And those will probably have a very high masses. So those are the things we are actually pursuing, trying to look for maybe a dark matter candidate, which is essentially invisible. You have to see, or maybe evidence of something which is invisible when actually produced in the experiment, or there are other heavy particles which like a mirroring image, but except the mass is heavier compared to the existing particles we know about.
So there might be totally new types of particles that we've never seen or imagined, but the Standard Model only has a few things in it. Maybe it's just a small representation of what's really out there.
Oh, yeah, absolutely. And actually, we know there are new things. As Sudong mentioned, we know there's dark matter. We look out and see how our galaxy is rotating, and we can see there's more mass there that we cannot see. We can see its gravitational effect. And there's a lot of reasons to think that the LHC may actually be able to produce the dark matter particle. And then, as Sudong mentioned, what you would see is the lack of anything.
Now, what are the practical benefits of this research? We're always looking for more energy to feed our industrial economy. Is there some energy locked up in these particles that maybe we can tap in a way that's more efficient than nuclear fission with uranium?
Well, I think it's difficult to think of exactly how you tap into it at the moment. But I think as time goes on, people will probably find interesting ways of how to relate to that energy, and maybe there's a way to utilizing it. But at the moment, I think this still is more of fundamental physics, and we'll see just what it is and how to utilize it. I think may take some more time, say the next generation of people gradually coming out with ideas to how to utilize it.
Now, some people say that CERN is really a great exercise in international collaboration, and just the kind of teamwork involved in the free scientific exchange has a lot of value in itself. Apart from the actual discoveries, just the basic culture of CERN makes a major contribution.
Yes, it's actually very interesting, I think, how CERN came together, given that the role of each country probably within the world scene is limited. But when CERN came together, I think is a very interesting model for international collaboration, with all the states in Europe come together to make a very large international organization. They can pull enough funding and human resource together to create a big project like this, which will be very hard for individual country to produce that. And that set a very good precedent, I think, at how these collaborative international collaboration can actually utilize the resources of the world to actually produce these scientific results. Otherwise, it would be just impossible to achieve.
Yeah, this is extremely expensive. Obviously, a ring 17 kilometers, 27 kilometers in circumference, that's pretty big. Is it hard to squeeze money out of governments for this sort of thing?
Yes, this is actually a big international treaty which actually set up CERN to actually allow this to happen. And also, is very interestingly, every other year there will be some country decided maybe we cannot afford to pay the subscription and so on. There will be some debate and so on, but invariably people come back to the same table to say this is important enough for Europe as a whole, and then things will continue as it used to be.
That's really actually one of the really fun things about being a physicist, that you meet people from all over the world, you work with them, they all have the same goal.
And we're going to have to wrap on that note because we are out of time. I'd like to thank my two guests for being here today. Sue Dong, experimental particle physicist at SLAC. Peter Graham, theoretical particle physicist, Stanford Physics Department. Thank you for watching. Visit us at www.futuretalk.net. For Future Talk, I'm Marty Wasserman. We'll see you next time.